题目也是40，题目也40多，然后我拿这个一包，你这么快都没事。
Okay, so for this, okay, I don't know what's going on there. So for this question, I assume that you guys know from E&M how to solve this because this is quite general. So the solution is basically H alpha beta is equal to minus 16 pi. No, 16 pi over 4 pi, which is minus 4. Right? So how you do this, you just do minus 4. And T alpha beta, remember I said everything here is constant. So this is a constant. So I can just take out T alpha beta and integrate this over a sphere. So this would be r prime squared over r minus r prime. And then I can take 4 pi out. So this will just be 16 pi again. Right? And then what happens is, I don't know, maybe perhaps you know how to integrate this, but let me do it once. U equals r minus r prime, du equals dr prime minus dr prime. Right? And then what we do is now we basically change this to u plus r minus u over u du. Oh, but it's squared. Sorry, it's a square. R prime squared. So this is just r squared minus a squared, u squared, sorry, u squared, plus u squared minus 2ru over u integral. And this is simple. So this one is just ln r squared ln u. This one is just u squared over 2. And this is minus 2r u, right? And you just substitute the u definition back. So this one is quite easy. And the next one, I don't know how difficult that one is. So this one, I'm sure that he will ask, because if you have a radial null geodesic, so if these two are constant, then d theta equals 0, d phi equals 0. So what you do is just 1 minus 2m dt squared plus r squared. This is equal to 0, right? So now what you do is you just multiply both sides. And then, well, you move this to the other side, you get dt squared equals dr squared over 1 minus 2m over r squared. Take the square root, dt equals plus or minus dr 1 minus 2m over r, and you integrate. So this is just simply t equals constant plus or minus this is multiplied top and bottom by r, integrals r over r minus 2m dr. And then we do the same thing, u equals r minus 2m, du equals dr. Then the above is u minus 2m over u integral du plus or minus constant. And then what is this is just integral of 1 minus 2m over u du const. And then what this is, it's t equals constant plus or minus, this is just, sorry, u minus 2m ln u, and u is r minus 2m, so this is just t equals constant, plus or minus u, which is r minus 2m, minus 2m ln r minus 2m.
Sorry.
Yeah.
How can you take the square root to dt squared and dx squared to dt and dx?
Oh, you just, because this dt squared is just dt times dt, but the thing is you need to take the plus or minus, because when you take square roots, you always have the plus or minus.
Oh, but dt squared is equal to 2t dt, right? No. dt squared
No.
is dt times 2t.
Yeah, no, that's the definition.
That's how you
write it. Yeah, it's just a really dumb way to write it. Yeah. Yeah. So dt squared is just dt all squared. So that's why it's a silly thing. Yeah. But yeah, that's how you get. So basically these are called null coordinates. So actually, if you write it, the Schwarzschild metric in these coordinates, you will find that the singularity here disappears. So, and the reason is in relativity, remember the whole point of relativity is everything is observer relative. So if you change your set of coordinates, you see a different thing. So in the normal coordinates, since I know a lot of people here are doing astrophysics, we use this Schwarzschild coordinates because it corresponds to an observer outside the black hole. But the coordinates here that we derive are called null coordinates, and it corresponds to an observer going into the black hole. So basically, outside the black hole, when you see an observer, there's no problem, because outside the black hole, when you see someone going into the black hole, you'll see the guy kind of freeze at the event horizon, and that's normal. But if you're the guy going into the black hole, everything is fine. Like you can go through the event horizon smoothly. The only problem is when you get to r equals 0, and they will never ask you to prove this because you can do it, but it's very difficult. R equals 0 is a singularity you cannot remove. So yeah. And maybe the next question is not really relevant because he doesn't ask you to solve in.
But there's an assignment question that's similar to this.
Kruskal? This one?
Yeah, Kruskal coordinates.
Okay.
But it's not from the point of view of a maximally extended coordinates.
Okay, so maybe I can show you why.
He basically gave us the coordinate transformation.
Okay, but he probably didn't tell you why you make this coordinate. The reason why you do it is very simple. Because in this natural log, there is a singularity at r equals 2m. So to get rid of this, you just put e to the power of this to get rid of it. You see? So the null coordinates are actually u equals t minus 2m ln r minus 2m, and then v equals t plus 2m ln r minus 2m. And the reason why you make this set of coordinate transformations is because what you do when you do this is you remove the singularity at the event horizon. But it's not maximally extended because there's still a problem when you set r equals to 2m or less. So that's the problem still remains in these two. So what you can, in principle, do is just put e to the power of this to get rid of the ln, and that will solve your problem. And that's why when we do it in Kruskal coordinates, there's an e to the power here, because you exponentiate the problem that you get. And miraculously, actually, this still satisfies the end. But he didn't teach Penrose.
No.
In Penrose. Okay. So maybe if you want to hear about it, I'll tell you later. But I think it's not so important right now. So actually, I want to talk about killing vectors. The reason why, it's because it can actually tell you the geodesic equation in one line if you know how to do it, if you know how to do it properly. But let me do the first part where it says it's asymptotically flat. So okay, so this is kind of like, if you know your approximations well, it's quite good. So delta over rho squared. So this is of order r squared. This is also of order r squared. If you set this to infinity, this quantity is of order 1. So the dt term is of order 1 here. But the and in here, this term is of order a squared. Here, this term here is of order 1 as well. But what you will see is, let's also examine the other terms. So here we have the same term. This is of order 1 because they're both of r squared. So this term, we keep this term. So in principle, dt squared, delta over rho squared, in the asymptotic limit is dt squared, if you set r to infinity, basically. And then here, rho squared over delta, dr squared, also preserves dr squared, because these two have r squared in the numerator and denominator. So, but the problem here is we have another rho squared d theta squared, and in the asymptotic limit, this r squared term dominates. So it would be r squared d theta squared. And now we have to look at the tricky term, which is the d phi squared. So d phi squared is, let's see, d phi squared. So this term here, you'll see this d phi squared term. So it has a sine squared over rho squared, but inside.
We have a good meeting.
Yes, I know. At 2 o'clock though.
Yeah.
I'll leave as soon as possible.
Oh, no problem.
Don't
If
worry.
you leave the condition.
Of course, of course.
Sure, thank you.
But you have to tell Mandy that. Yeah. So we have this, and we have r squared plus a squared, and then we have d phi out here. So this is the somewhat troublesome term, but you can see that this has a rho squared here, and this is just constant. So actually this rho squared term will dominate because it has the r dependence. So this term actually vanishes in the asymptotic limit. And this one has r squared. This one is of order r squared. This term. But there's another squared term. So this is of r to the 4. But r to the 4 divided by rho squared is of order r squared. So this would be r squared sine squared theta d phi squared. So this term here is of order this. So in the asymptotic limit, it becomes Minkowski. So there, I remember you guys had a homework question, and I wanted to show you how to do it in one step. I remember it was 30 marks. And by showing you how to do it in one step, I think it's,
Geodesics.
yes, it's a really, there's a cool trick to do. So I have to open it up though. Give me 1 second. So the metric was like this. The metric was ds squared. Right? So you want to find the geodesic. The question asks you to prove that t dot is equal to b e to the x over a. So to do this, I showed you how to do it using the Euler-Lagrange equation, but what I can show you how to do is also to do it using killing vectors. So what a killing vector is, okay, let's do it for this simple one. So a killing vector, just look at the metric and see what it doesn't have. So it's in t and x coordinates, right? So what variable doesn't it have in front of the coefficients? It does not have a t term, right? So the killing vector is the t killing vector. So the killing vector is this. So I'll denote it by k. So k is the killing vector. The t killing vector is 1, 0, because this is t and x. So since the x one is since there is an x dependence, the killing vector of x is 0. And since there's no t dependence, you want to keep the t1. So what's an interesting fact is the killing vector is conserved along the geodesic. It's conserved along the null geodesic. So k, the killing vector, times the 4 velocity is always equal to a constant. So, but remember, we have to be careful. If we want to lower the index, we don't just simply multiply by the Minkowski metric. We have to multiply by the actual metric. So this would be K of t ut, but we want to raise this index. So this would be kt ut g, oh no, is that right? gtt. So this would be we extract this minus e to the minus x over a times, and the t for vector is just t dot is equal to a constant. And this means that t dot is equal to a constant times e to the x over a. So if you know what the killing vector is, remember that question that you guys had? You had to do many steps. If you know what the killing vector is, so you search for look at the metric, see what it doesn't have. It doesn't have t dependence. So you know the t killing vector is the one that you want. And then you multiply by the forward velocity to get the result that you want. So this is an extremely fast way to get the geodesic equation if you know how to use the killing vector. So you look at and killing vectors are really important because they tell you what quantities are conserved. So in this case, since there's no time, and you can always write this as Lagrangian, remember. And if the Lagrangian is time independent, that means its energy is conserved. So the energy of this system is always conserved. But since it has an x dependence, it means the linear momentum is not conserved. So that's the physical meaning behind killing vectors. And here, for the Schwarzschild metric, the killing, so basically, since it has an r dependence, then the r killing vector is so the only thing that's conserved here is the energy, because there's no time dependence in everything. But since it has a dependence on r, the energy,